Okay, this is the first video of Unit 13, Acids and Bases. Please let me know in the comments if you can hear this, if you can see this just fine. We're trying some new hardware and software, and, well, this is for you guys, so you tell me if you like it or not. Here's your objectives for not just this video, but for the entire unit. You need to know how to write the chemical formulas of common acids and bases. You need to be able to distinguish between types of solutions such as electrolytes and non-electrolytes, define acids and bases, and distinguish between Arrhenius and Bronsted-Lowry definitions for both, and predict the products of acid-base reactions that form water. You need to understand and differentiate among acid-base reactions, among others. You need to define pH and use the hydrogen or hydroxide ion concentration of a solution to calculate its pH, and also distinguish between degrees of dissociation for strong and weak acids and bases. We're going to start by talking about some properties of acids and bases. You can see on your note page right there, you've got room to put some of these on the left side for acids and some on the right side for bases. So I'm just going to run through these real quick and then come back and talk about them in depth in a minute. First of all, both acids and bases are electrolytes. As far as taste, normally you shouldn't taste anything in the laboratory, but for those acids and bases that we use as food, acids have a sour taste, bases taste bitter. Acids turn litmus paper red. Litmus paper is an indicator, and there are several others, but that's just one. Bases turn litmus paper blue. Acids react with metals to give off hydrogen gas. Bases don't react with metal. Acids don't really have much of a feel beyond just kind of feeling like water. Bases feel very slippery. You can find acids in things like vinegar, sour milk has lactic acid, soda, any kind of fruit that has a sour taste, pickles, yogurt, basically anything that you eat that tastes sour has an acid in it. Some bases you come in contact with are things like ammonia, which is a cleaner, lye, which is drain opener and oven cleaner, very strong base, antacids, baking soda, baking chocolate. If you've ever tasted baker's chocolate or cocoa, it's got a very, very bitter taste, and so on. On the pH scale, which we'll talk about more in a minute and then more in a later video, acids have a pH less than 7, bases have a pH greater than 7. And then acids, one way that they're defined is that acids are substances that produce hydrogen ions in water, whereas bases produce hydroxide ions, OH ions in water. Just a reminder, you should remember this from our last unit on solutions. An electrolyte is any substance that when you put it in water, it dissolves, it gives off ions, and it can conduct electricity. Now, depending on how well something ionizes, how well it gives off those positive and negative charged ions, lets you know how strong or how weak of an electrolyte is going to be. Here's a picture of the pH scale. Right here in the middle, you've got pH 7. That's neutral. Anything less than 7 is acidic. So, for example, here you've got rainwater. It's slightly acidic. Wine is about 10 times more acidic than rainwater. Lemon juice is about 100 times more acidic than wine, and so on. Those are just a few. There are several indicators. An indicator is any substance that changes color when it's in the presence of an acid or a base. Litmus paper is one of the more well-known ones. Acids turn blue litmus paper red, turns it pink. Other indicators are things like cabbage juice, which we've mentioned in a previous activity in class. Acids react with metals to give off hydrogen gas. Now they also form what are called salts. Now this isn't necessarily table salt like you put on food. A salt is just an ionic compound of a metal with a nonmetal. So you can see in this example right here we have hydrochloric acid reacting with magnesium metal. One of the products you get from that is hydrogen gas. This is why when you put metals in acid they bubble. That's the gas that they're giving off. And you see the other product is magnesium chloride. This would be the salt in this reaction. Now, this is something for you to think about, maybe tell me later in class. How can you tell that the bubbles being given off from a reaction like this are hydrogen? What's a test you can do? Acids also react with carbonates. Carbonate or bicarbonate are negative ions which have carbon and oxygen in them. This is a classic example right here. This right here is acetic acid, HC2H3O2, which is the main ingredient in vinegar. This right here is sodium hydrogen carbonate or sodium bicarbonate, which is baking soda. And if you've been paying attention at all to science ever since the elementary school years, you should know that when you put vinegar and baking soda together, you're going to get a pretty strong chemical reaction. And one of the things you're going to get are lots and lots of bubbles. And you can see from these products right here where that comes from. Here's your bubbles. It's carbon dioxide gas. Water is another product. And you're going to see this show up an awful lot. Anytime you've got an acid and a base reacting, one of the products you get should be water, okay? Because that's when the acid and the base neutralize each other. This right here would be your salt. This would be sodium acetate. Another thing you hear about quite a bit when you talk about acids is acid rain. Some substances, especially things like sulfur dioxide, when they're released from factories, usually by burning fossil fuels, oftentimes they will react with water vapor that's already in the sky to form sulfuric acid. When that sulfuric acid falls to Earth, it's called acid rain. Now, acid rain has about the same pH as tomato juice, okay? It's not real strong stuff, but over time it can do a lot of damage. This is an old photo of a calcium carbonate or stone statue of George Washington, and you can see after, several decades of acid rain, George isn't looking so great. He's kind of looking like zombie George Washington, which is actually kind of cool, but it's really kind of sad for that statue. Bases, on the other hand, have a pH greater than 7, so again, here's neutral, and as we go up, we run into several bases. Now, something interesting I think I should note here is that human blood is actually slightly basic. It's got a pH of about 7.5, which is just a little bit north of neutral. And it's important that your blood is basic instead of acidic, because if your blood becomes acidic, then you have all kinds of problems. It's called, I believe, blood acidosis, and it's really, really not good. Your body has a bunch of systems in place to keep blood acidosis from happening, and these things are called buffer systems, and we may talk about them later in class. You may talk about them later on in your life. I don't know. Baking soda, a little bit more basic, about 10 times more basic than human blood. Laundry detergent, strong soaps, is about 10 to 100 times more basic than baking soda. And way up here with household bleach, it's got a pH of 12.5, quite a bit more basic, and it keeps on going all the way to 14. Bases also affect indicators. In the case of litmus, bases turn red, litmus blue. A good way to remember that is B for blue and B for base. Another classic indicator of bases is phenolphthalein, which turns pinkish or purplish in the presence of a base. Real pretty kind of pink-purple color. And that's the end of our first video.